Welcome back to the deep dive. Today, we are strapping into the cockpit and focusing on a life or death calculation that pilots face when things go wrong mid-flight. How much extra fuel are we burning right now?
It sounds like a question that, modern aircraft should be able to answer automatically, right?
You think so?
We have these incredibly sophisticated computers managing every single aspect of flight. But the reality is, monitoring fuel consumption is one of the most critical tasks for a flight crew.
And we've talked about this before, a while back when we looked at that low fuel situation awareness research.
Exactly. And the core conflict here, the thing we're really digging into, is that when a serious system failure happens, the crew has essentially been flying blind.
Blind about their fuel, you mean?
Precisely. The flight management system, the FMS, it's the brain of the aircraft, and it gives you that estimated fuel on board the EFOB, but it only works under perfect nominal flight conditions.
And a major failure is anything but perfect.
Right. Those predictions just shatter the moment the aircraft moves outside of those conditions. The FMS, you see, it's trained for predictability. It currently only accounts for one major non-nominal condition,
Which is?
an engine out failure.
That's it. Just one. For all the things that can go wrong.
Just one. So for virtually every other in-flight emergency that dramatically affects the aircraft's physical shape, its aerodynamics, that FMS prediction becomes dangerously optimistic.
It just doesn't factor in a sudden massive increase in drag.
And we are not talking about small percentages here. I mean, before these procedural changes were implemented, there were documented failure modes, like
Right.
trying to fly with the landing gear stuck down,
Okay.
where pilots were literally instructed to multiply their fuel consumption by approximately 2.8.
2.8 times. That's a 180% fuel penalty.
180%. It's catastrophic if you don't calculate it fast.
Right, because the number on your screen, that EFOB, is now hic.
Yeah.
It's worse than useless. It's actively misleading.
It's a lie. The pilots need a quick, standardized way to figure out how far they can actually go.
So that's our mission today. We're going to unpack the safety revolution that really kicked off around November 2011 with the introduction of this fuel penalty factor, or FPF.
We're looking at the new procedures, the documentation, all designed to close this awareness gap and give the crew the hard numbers they need when the automation fails them.
Okay, so let's start with the basics, the physics of it.
Hmm.
Why does a failure suddenly turn this incredibly fuel-efficient machine into a total gas guzzler?
Well, at its core, it's simple. Any failure that disturbs the sleek, clean profile of the aircraft instantly increases drag.
So it becomes less streamlined.
Exactly. And that increase in drag has to be compensated for. To maintain your speed and altitude, the crew has to increase engine thrust immediately.
And if they don't have the spare thrust,
Then they have to descend to a less efficient flight level or
Right.
slow down, and both of those things radically change their fuel use and, their arrival time.
So what are the main things that go wrong? What are the primary culprits that cause this massive unexpected drag?
You can really break them down into two main categories.
Huh.
The first one is pretty obvious. Anything affecting the landing gear or their doors.
Right. If a hydraulic or electrical failure leaves the gear hanging out, that's like a giant air brake.
A gigantic air brake. It's hard to miss. But the second category is often more subtle and in some ways more dangerous.
Which is?
A failure in the flight control surfaces. So we're talking about the surfaces on the wings and the tail, your spoilers, ailerons, flaps.
And when those fail, they don't just, stay in place?
Not always. The aerodynamic forces on them can drive them into these really high drag configurations. We typically see it in three ways.
Okay.
First, a surface can get blocked in its full deflection. Pilots call that a runaway. Second, the surface could become free and just float in the wind, what's called the zero hinge moment position.
And that floating creates a lot of turbulence.
A ton of drag. And the third one, which I find particularly sinister, is something called spoiler drift. It's a failure that sort of creeps up on you.
Let's focus on that one because it sounds like it really illustrates the problem with just relying on automated warnings. So, spoiler drift, how does that start?
It usually begins after a hydraulic system failure. That means some of the spoilers on the wing are no longer powered.
Okay, but they should stay retracted, right?
They should. Aircraft like the A320 have what's called an anti-extension device. It's designed to mechanically lock that unpowered spoiler in place. But these devices aren't perfect.
What goes wrong with them?
Well, the servo control can be sensitive to temperature variations, or maybe there's a slow leak in the actuator, and that mechanical retainer can just slowly start to yield.
And as it yields, the air flowing over the wings starts pushing that spoiler panel up.
Exactly, pushing it out into the airflow, moving it toward its worst-case drag position.
This is where that silence becomes the killer, isn't it?
It is. So when the initial hydraulic failure happens, the crew gets a caution, and the affected spoilers show up as fault retracted on their display.
So they think, okay, problem contained, they're locked in.
Right. But here's the critical operational nugget, especially for the A320 family. If one of those spoilers then starts to drift, no ECAM warning, no master caution, nothing will appear as long as the extension stays below a very specific threshold.
And that threshold
It's
is
2.5 degrees.
2.5 degrees. That's tiny.
It is, but think about it. You have a failure that is actively increasing your fuel consumption, but you get no explicit warning. The FMS is oblivious. The master warning system is silent.
So the plane is bleeding fuel and the pilots have no idea.
Not until it crosses that 2.5-degree line. Then the amber FCTL SPLR fault caution finally triggers, and the spoiler is now indicated as fault deflected.
And only at that point is the increased fuel consumption considered non-negligible.
Correct. But that drift could have been happening for an hour before that. It just underscores why a flight crew can never, ever outsource their situation awareness solely to the automated caution system.
That point gets even more complicated when we talk about not just one failure, but combined failures. What if two small, seemingly independent problems collide?
That's where the complexity truly multiplies. The source material really emphasizes that faults that are individually benign,
So on their own, they don't cause any fuel penalty.
zero fuel penalty, but they can lead to severe overconsumption when they're combined.
So this is like a vulnerability in the redundancy of the system.
Absolutely. And this scenario often comes up when an aircraft was dispatched under MINLL rules, the minimum equipment list.
Right, the MEL. That's the list that says what can be broken on the plane and it can still legally take off.
Exactly. So you're taking off knowing you're already a bit vulnerable because you're allowed to fly with a system X or Y already inoperative.
So you launch with one level of redundancy already gone, and then you have another simple in-flight failure.
And the whole system can collapse into a high drag state.
The A330 example you mentioned makes this really clear.
It does. So in that case, if a secondary flight control computer fails by itself, there's no fuel effect, it's fine.
But
But imagine that plane had already been dispatched under the MAL with a primary flight control computer inoperative. It was already slightly compromised.
and when you combine those two failures, what happens?
The combination causes a critical control surface, the left outboard aileron, to immediately lose all power and control.
So it just goes limp.
It reverts to its zero hinge moment position, floating freely in the airstream, and that floating aileron immediately generates substantial uncompensated drag.
Meaning the crew now has a massive, unannounced fuel penalty that neither the FMS nor the individual fault warnings would necessarily account for on their own.
Exactly. They're stuck trying to figure out the compounding effects of two different problems, and that sets the stage perfectly for why the industry needed standardization.
Which brings us back to that revolution in November 2011, the fuel penalty factor procedures. So let's compare. What did pilots have before this versus what they gained?
Well, before 2011, the process was inconsistent. You had to do a lot of digging. Yes, for some failures, the ECAM status page would display increased fuel consump, but that was far from universal.
And it wouldn't show up for those complex combined failures we just talked about.
Never. And even if that alert did appear, the actual data, the percentage increase, was often buried somewhere else.
So in the middle of an emergency, you're having to go hunting through the Flight Crew Operating Manual, the FCOM.
Right. Cross-referencing alerts, looking for tables, unless it was one of the really big, obvious ones covered in the Quick Reference Handbook, the QRH.
Like the jam flaps or the landing gear being stuck down.
For those, the QRH procedure itself gave you a specific multiplier, but the magnitudes of those multipliers really underscore the danger. We already mentioned the landing gear.
Multiplying consumption by nearly 3. 180% FPF.
Imagine being over the mid-Atlantic and realizing you need nearly 3 times the fuel you thought you did. Or landing with both slats and flaps extended. That required multiplying fuel consumption by 2, a 100% FPF.
It's a huge operational shock. So the new approach in 2011 was all about standardization.
Standardization and centralization. All the fuel consumption increase information is now gathered in one dedicated, easy-to-access place.
The in-flight performance chapter of the QRH.
The FPE-FPF chapter
Yeah.
specifically. And this is all built on two powerful new tables designed to catch every scenario.
What are they?
First, you have the ECAM alert table. That's your simple entry point for active, straightforward failure alerts. But then, and this is the key, you have the INOP SYS table.
And that's the safety net.
That's the safety net. It's designed specifically to cover those combined or MAL-related failures where the consequences might not be immediately obvious.
And there's a cutoff, right? They don't list every tiny thing.
Smart cutoff. The tables are specifically limited to failures that lead to a fuel consumption increase greater than 3%. Anything smaller is considered operationally insignificant. It keeps the focus on what really matters for safety.
Okay, so let's get to the critical part. The procedures are standardized, but the calculation itself still requires the crew to be active. How do they actually use these fuel penalty factors?
So the procedure is very rigorous. After the crew has completed the immediate urgent ECAM actions, they have to shift into what's called a situation assessment.
And that's when they turn to the QRH.
They are formally directed to refer to those FPF tables if the status page shows increased fuel consump, or if they see any flight control surface or landing gear component listed in that INOP SYS section.
And this is key. They'd have to check both tables, even if they only had one active alert. Why the dual check?
That dual check is the insurance policy against those combined failures. The INOP SYS table is there to catch the systems that were broken before takeoff, the MNLL items, or to catch a failure that by itself doesn't trigger a fuel warning. By checking both, you ensure you capture all the additive penalties.
And the final formula is actually pretty simple, which I imagine is crucial under pressure.
It is simple. Once you have the FPFs from the tables, you calculate the required additional fuel. The formula is just your fuel on board minus the estimated fuel on board at destination times the fuel penalty factor.
And if there are multiple failures, you just add the factors together.
That's the beauty of it. They're simply additive. If failure A gives you a 5% FPF and failure B gives you an 8% FPF, you just apply a 13% penalty.
Okay, let's walk through that real-world A320 example again, because that 18% penalty is huge. So the flight was dispatched under MLL with one flight computer already out.
ELSC, one IMP, yep. And then in flight, they get a hydraulic caution, HYD GSYSLOPR.
That combination leads to the immediate loss of the left aileron, so they go to the tables.
First, the INOP SYS table. For the loss of that left aileron, they are instantly given an FPF of 8%.
8%. That's already substantial. Then they check the ECAM alert table for the hydraulic caution.
Right. And that gives them an FPF of 10%. But, and this is important, only if the affected spoiler is indicated as extended.
Meaning it's drifted past that 2.5-degree silent killer threshold we talked about.
Exactly. So if the spoiler has remained retracted, the total penalty is just the 8% from the aileron. But if that spoiler's out, they add them up.
8% plus 10%. The total fuel penalty is 18%.
18%. That's nearly a fifth of your remaining flight time or your contingency fuel just vanishing due to a series of cascading failures. And the FMS would still be telling you everything is fine.
It's why this manual formalized process is so vital. It forces the pilot to be the final cross-check on the automation.
And this is getting even more support from technology now. The sources mention future updates to the flight warning computer itself.
Right, to flag these issues even more clearly.
Yes. Starting around 2012 with new aircraft standards, the automated system began to detect all failure cases leading to a fuel consumption increase of more than 3%, including the complex multiple ones.
And the best part is the explicit messaging. What does it say?
Well, when that failure is detected, the system won't just display fuel consumed in CRSD. It will also immediately show a clear, powerful line on the ECAM status page. FMS Pred Unreliable.
FMS prediction unreliable. That's about as direct as you can get.
It's huge. It's the automated system telling the human crew, I am broken, do not trust me, refer to your manual procedures. That's the ultimate confirmation that the pilot has to drop the automated prediction and immediately turn to the manual QRH procedure.
So what we've really detailed today is this complete procedural and technological overhaul. It's designed to address a hidden danger in aviation. By centralizing all the fuel consequences and formalizing this dual table assessment, it's just a major step forward.
It really is. It ensures that every flight crew, no matter how complex the failures they face, has the same standardized, formalized procedure for assessing the fuel consequences. It closes a very dangerous gap where the automation was simply out of its depth.
And that leads to our final thought for you to consider. We spend so much time talking about how automation is taking over the cockpit, making everything faster, more efficient.
Mm-hmm.
But this entire system, the fuel penalty factor,
Yeah.
it exists because the core automated flight management system fails exactly when pilots need it the most during an emergency.
It really underscores the critical, permanent role of the human operator. Even as technology advances, complex safety protocols still require humans to perform manual, critical thinking calculations when the automated systems become unreliable. The machine can flag its own limitations, but it still takes the pilot to apply the factors, to manage the remaining resources, and to ensure they have enough fuel to get to their destination safely.
It's a powerful reminder that vigilance can never be automated.
No.
A perfect place to end this deep dive. Thank you for joining us. We'll see you next time.